Hi all, welcome. This is a very special session of our CAE Spring Seminar Series. In that we will have four PhD students talking for about 11 minutes each and a lot of Q&A. So our speakers are going to be Sofiane Amroun, Sadegh Tale, Austin Perry, and Kyrah Williams. And they're all working on various different topics going from mechanochemical activation, molecular design of non-ionic surfactants, simplified wastewater infrastructure, and an analysis of water conservation. So thank you very much to our speakers. Thank you to your audience, and we can get going. So Sofiane, your first 11 minutes.
All right. Can you see my screen well?
You need to full screen. Yeah, perfect. Thank you.
All right, awesome. Thank you, Pranoy. Thank you, everybody. So I'm Sofiane Amroun. I'm a third year PhD candidate here at the University of Miami, working with Pranoy. And today I'm going to be talking about one of the studies of my PhD thesis, which is mechanochemical activation of basaltic fines for the production of supplementary cementitious materials. So a little bit of background. Cement production. Cement, as we know it, is main ingredient in concrete. Concrete is the second most used material in the world. To produce this cement, we typically mix around 20% of clay and 80% of limestone, which is mostly CaCO3. We get the materials at a quarry, we crush them, and we homogenize them, and then we heat them up in a kiln to about 1450 degrees Celsius to produce the clinker, which later on will be crushed and blended with other materials to give us the cement as we know it. At the kiln, the temperature is about 1450 degrees Celsius. At around 900 degrees Celsius, we have a reaction that happens, which is decomposition of CaCO3 to give us CaO plus CO2. And the CO2 that's emitted here is approximately 60 to 65% of all the emissions that come from cement plants. The other 35 to 40% are fuel combustion, crushing, and grinding. And the cement produces about 5 to 10% global man-made CO2 emissions. One solution to this is to replace cement partially with other materials that we call supplementary cementitious materials, which are typically aluminosilicates, often with a high amorphous content. Amorphous meaning that the atoms are not structured well, which is the opposite of crystalline structure. So these SCMs generally improve long-term strength, durability, sustainability through different ways. I'm not going to get into the details here, um, but typical used SCMs are, for example, fly ash. I'm pretty sure most of you heard of fly ash or slag, which is the blast furnace slag, or silica fume. The issue with these SCMs is that we're in short supply. A lot of you have seen this figure in the past. So if we look at the fly ash, how much we have and how much, and then when we compare it to the amount of cement that's produced every year worldwide, we see that we have very short amounts of these materials. So other materials are necessary, and typically people use clays. For example, there's the renowned limestone calcined clay cement, which is the LC3, which is a type of cement that has a high content of clay, like 35%, reaches 35% and 15% limestone. But the issue with these kind of materials, which is the clays, even though we have a big supply of it, is that we need a specific type of clay, which is kaolinite, at an amount of at least 40% to have uh, strength, durability, that's comparable to the PLC or even better, especially the strength. Durability is better, but the strength, yeah, we need high kaolinite content. So for my research, instead of using clays, I use filler materials which fall under this category, and we have enough of them in the world. I'm using basaltic fines for my research. But basaltic fines, as they are inert materials, and we need to activate them so that they can actually react with the cement, some cement phases, to give us more strength and more durability. The typical way to activate the materials is thermal activation, just like we do for clays. We do calcination, which is thermal activation using heat, to go from a crystalline structure to an amorphous structure, and dehydroxylation and all these details which make our material more reactive. For my research, I don't use thermal activation. I use mechanochemical activation. And we are actually able to change the structure at the atomic level of these materials from crystalline to amorphous, which make them more reactive. And when we have a more reactive material, we can um, replace more cement with it and get the strength that we want for our concrete. The issue now with the mechanochemical activation, that it's not well understood like thermal activation. Thermal activation, we understand it pretty well, but when it comes to mechanochemical activation, not really. So you might be asking ourselves, how does this work? How do we activate the materials mechanically? Well, there is a million ways of doing it. The idea is just to input as much mechanical energy uh, as possible into these materials. And the way that I use is planetary ball mill, which is the one you see in the right image. This is the actual one that I use, and this is how it works. So we have our powder, and we have the grinding beads, and then it spins it at very high RPM. I use 400 rotation per minute. Um, yeah. So what I did is that I took a basaltic fine with the chemical composition here. It's mostly silica, alumina, and iron, a little bit of magnesium and calcium. I put it in the planetary ball mill. The grinding speed, 400 RPM, I didn't change the grinding speed. I changed the grinding time, so 15 minutes, 30 minutes, and 60 minutes. And I also changed the ball powder ratio, which is an important parameter that measures the weight of the balls, so the grinding media, divided by the amount of powder that I put inside the jars. So I have the ball powder ratios of 5.2, 7.7, 10.3, and 20.6. And these came from dividing the ball weight divided by 30 grams of powder, 60, 80, and 120 grams of powder. So here we have the ratio of these weights. So after activation at these different parameters, I get like different materials with each combination. And on all these materials, before and after activation, I've done SEM, which is scanning electron microscopy, X-ray diffraction to look at the phases and the degree of amorphization, the BET specific surface area to have an idea about how fine these particles are, and also the porosity of these materials. And we also ran the modified R3 test, which is a test that mimics the environment where these SEMs are going to be when you mix them with the cement. And so the reaction is going to happen between the SEM and those cement phases and release heat. And that's the heat that we measure using this test. And from the heat measurements, we can say a lot about the performance of our SEM and the effectiveness of the mechanochemical activation. We ran other tests, but I'm just gonna be talking about these four ones in this presentation. So the scanning electron microscopy images show the following. So the raw basaltic fines are in the image on the left, and we see that these materials, these particles are very rough and angular. While after activation, we see two types of particles. So we call these aggregation, which is when very fine particles come together. And we also see agglomeration, where we have particles, large particles that are very similar to the raw basaltic fine particles, surrounded by very small particles. For the surface area, this is the grinding time. At the beginning, from zero, this is the raw material, and this is 15 minutes of grinding at different ball to powder ratios. We see a huge increase in surface area because our material is just getting, like the particles are getting smaller and smaller in this region here. So crushing happens here, and then afterwards we're getting aggregation and agglomeration that we saw in the SEM images, and then we see decrease in the surface area. For the XRD, the black curve that we see here is the raw material. These two are the same. And XRD, in XRD, the sharper the peaks, that means our material is, in general, more crystalline. So the structure of our atoms is well organized. And so this is for a BPR of 5.2. This figure is for a BPR of 5.2, and this is 20.6. And this is 15, 30, and 60 minutes for both figures. And we see that with grinding time, the peaks, actually, the peak intensities go down and they get broader, which means that we're getting amorphization, and we were actually able to estimate the degree of amorphization. So the raw material is 14, and with the BPR 5.2, we're able to reach 39, and with the BPR of 20.6, we're able to reach 77. For the modified R3 results, I'm showing here the 72-hour heat release. So after 72 hours, we measure the heat release, and I plotted it here for the different combinations of the parameters. So this is the grinding time, and then for different colors, it's different BPRs. So we see that with an increase in grinding time and with an increase in ball to powder ratio, so we would have less powder inside the jars, we see that there is an increase in heat release. For fly ash, I talked about fly ash earlier, which is a material that's usually used as an SEM. We typically have a heat release of about 200 to 250 joules per gram SEM. So with mechanochemical activation, we were actually able to reach higher reactivities than typically used materials like fly ash. This is the last figure I'm going to show in this presentation. In the x-axis, we have the degree of amorphization that we measured through the XRD data. And here the heat release of our reaction from the modified RT test. And we see this beautiful correlation here with an R squared of 0.94, which tells us that the reactivity of our material is mostly driven by the degree of amorphization. So for conclusions, we can say that mechanochemically activated basaltic fines can be used as a source of SEMs, as we saw from the modified R3 results. And we also saw that longer grinding and higher BPR increase the reactivity, and that amorphization is actually the parameter that mostly drives the reactivity of mechanochemically activated basaltic fines. And thank you very much.
Fantastic. Thank you for also sticking to time. We have a time for a couple of questions, and then we can do questions later at the end if we have time.
Hi, great presentation, Sofiane. I have just a couple of questions. Hello?
Yeah, go ahead.
Yeah. So first of all, I just saw the ball to powders ratio 5.2, 7.7. So like, how did you fix this ball to powder ratio? Like, was it like kind of optimized to trials and errors? And how is it? Like, how did you fix this?
Yeah, so for the BPRs, we first of all check the literature, and we've done some trial and error tests. In literature, usually people use BPR from like 1 to 25, and I've seen more and less, but usually like between 10, I would say, and 25. That's where I started, and basically the BPR values that you see are just a ratio of the weight of the balls to the weight of powders. We kept the number of balls and their size and the material of the balls the same, so the exact same balls, but we changed the amount of powder we put inside the jars. So we use 30 grams, 60 grams, 80 grams, and 120 grams of basaltic fines inside the jar. So after you calculate the ratio, it gives you those values.
Oh, okay. Thank you. And another thing which I was thinking is for different the parameters here is ball to powder ratio, the grinding time as well, and the RPM as well. So what I was thinking, if it's all related to the energy input, even if you're grinding it for a lower time but higher in RPM, so you have a certain energy input, and if you are grinding it for a less RPM but for a higher time, you have a like almost you can have a similar energy input. So is it the energy input which is driving the amorphization, or like yeah, like it could be interesting to see that, like if we can correlate all this, the energy input that is driving the amorphization.
Yeah, so good question. We didn't look into the like changing the RPM, but
Mhm.
we believe that what's driving the mechanochemical activation is how much mechanical energy actually goes
Mhm.
to the material. And throughout the grinding process, you will have a lot of losses, loss in energies,
Right.
loss in heat, and like inefficient collisions,
Right.
or anything else. So I'm not sure about how like varying the RPM, for example, would affect how efficient the grinding is compared to like changing the grinding time or the BPR. Yeah,
Okay. Thank you, Sophie.
you're welcome. We can't hear you, Pranay.
Yeah, thank you very much. We will move on. We can come back later at the end. Sadegh. Thank you, Sofiane.
You're welcome.
Can you see my slide?
Perfect.
Okay, good morning, everyone. I'm Sadegh Tale. I'm a third-year PhD candidate in the College of Civil and Architectural Engineering. I'm happy to present to you our project, which is trying to predict the air entraining of non-ionic surfactants using their molecular properties. Okay, so the problem at hand is that if you have a wet climate that can go through cycles of freezing and melting, concrete structures sustain a lot of damage. And this is primarily because water can seep into concrete, and when it freezes, it exerts some hydraulic pressure on the matrix, which through cycles can really damage the concrete. You can see here roads, bridges, basically all concrete structures are susceptible to this kind of damage. And we know the solution to this. We add some chemical called air entraining agent to concrete, which basically increases the void volume inside. And these voids basically can act as hydraulic exhaust for the pressure that is building inside the concrete. The way the researchers develop these chemicals is that they make a small adjustment in the molecular properties of these chemicals, and we have a very good idea of what type of structure, chemical structure we want, right? So they make a small adjustment, and then they have to go through a lot of different tests to see if these air entraining agents work at all, and then to see the compatibility with different parameters that they have. This process can be time consuming, it can be expensive, and overall it's very labor intensive. So that's why a lot of researchers are turning towards statistical methods and machine learning to try and expedite this process. And this is basically what we want to do in this project. We want to take the molecular properties of any molecule or surfactant and then predict if they are a good air entraining agent for cementitious materials, specifically cement in this case. There are some consideration with any data science implementation of machine learning. We are limited by the number of data that we have. There is no data set that gives us the type of information that we want. So we have to develop our own data set, which can be very expensive, very labor intensive. So we have a relatively small data set. The other thing is that we are trying to bridge a large gap, right? We are going from angstrom or nanoscale, which is the molecular properties, molecular weight, and so on, all the way to centimeters and decimeters. This is a huge gap that we're trying to navigate. So we took some steps to try and address this. This is the overall scheme of our machine learning model. It is composed of 3 layers. In the first layer here, we have the input information, which, as I mentioned, are the molecular properties of these surfactants. Things like hydrophobicity, molecular size and weight, length of hydrocarbon chain, and some other stuff that are not present in this figure. On the second layer, we have the physicochemical properties of these molecules in solution. So when you dissolve them, how much surface tension do they have? What is their particle hydrophobization like? How much foaming they have? What is their foaming stability like? And so on. And then on the third layer, we have the output, which is the macrostructural properties of these surfactants in hardened concrete. This is an overview of the properties that we have, but I'm going to go through that later on. So to develop our data set, we contacted a lot of different chemical manufacturers, and we were able to get 59 surfactants in total. These are mostly alkoxylates, meaning that they contain ethylene glycol in their structure. They're also all non-ionic, so they don't have any surface charge. As a result, their absorption to particles is relatively low. Okay, so I'm gonna go through the layers. These are the properties that we have on the first layer. Things like hydrocarbon chain length, which is a good indication of the overall hydrophobicity of the system. We also have HLB, which is short for hydrophobic lipophilic balance. Basically, it tells us if a molecule is very hydrophobic or very hydrophilic. We have molecular weight of these surfactants. Molecular weight is very important in terms of packing density at interfaces. Basically, these molecules will go to the air-water interface, and their size can dictate how much packing they have there. Generally, we want molecules to pack more densely at the interfaces. It can give better results, but nevertheless, molecular weight is an important factor. It is also important in terms of its dispersion of these molecules in the solution. We also have cloud point, which is, again, important in terms of solubility and foaming. All of these parameters that I'm showing here are parameters that are generally prevalent in the industry. On the second layer, we have the physicochemical properties, things like foam volume. When I say foam volume, I mean both the initial foaming capacity and foaming stability. So how much foam they can make and what is the stability over time. So if we have a chemical that makes a lot of foam and then all of those foams disappear in 2 seconds, that's not generally a good foaming agent. So that both of those parameters are important. We also have surface tension, which is known in literature to be a very important parameter in terms of air entraining. We also looked at the interfacial properties. So when these surfactants go into the air-water interface, they can give some viscous and elastic properties to these interfaces. And a lot of properties of the bubble, such as their stability, is dictated by these viscoelastic properties. We measured these properties using the dilatational rheology of interfaces, and we saw some interesting results. We decided not to include those in this study, but nevertheless, it was very important to see that. We also looked at the Pickering stabilization of particles. Again, particles can go on the interfaces and they affect the stability of interfaces. And this property is kind of hard to measure. So we measured it indirectly using contact angle. So we measured the surface contact angle on hardened cement paste to see the change in hydrophobicity of these particles. Finally, on the third layer, we have our macrostructural properties, things like the total air void volume, the void size, and the distance between these voids. And we did that using Microcity, which gives us a 3D model of our hardened cement paste that then we run a lot of different analysis on, and we can get a plethora of different information. So this was our data set building stage. After that, we did pre-processing and processing on those data. So for example, here I have some a sample of those steps that we did. Here you're seeing the outlier detection algorithms that we ran on the first layer on the left and the second layer on the right to detect the points that might be outliers in our data set. After that, we developed an algorithm, an iterative algorithm that goes through the data, does feature selection, trains the model and selects the best algorithm to train the model, takes care of overfitting by regularizing the model. And that was very important for us, not to overfit the data and get some model that performs really well in terms of metrics, but cannot predict the performance that we are looking for. So we use this algorithm, and this is the final results in terms of in training prosody. So here you see the training and testing data set, and this is the validation data set. Here you see that, for example, in terms of training prosody, our RMSE is around 3%. In comparison, we also developed a model using one of the AutoML training packages, and you see that performance here as well. Our model seems to be performing relatively well, and we should keep in mind that going from molecular properties all the way to mesoscale concrete properties, 3% is a really good number. Some interesting results that some interesting patterns that we actually saw in our data set, I've listed here. In terms of surface tension, surfactants that had an HLB from 7 to 15 seem to be performing relatively well. Surfactants that were too hydrophobic or too hydrophilic had higher surface tension, which is interesting. So we need a balance in hydroplasticity in order to achieve the lowest surface tension. And this is surface tension in cement pore solution, not DI water. Also, in terms of molecular weight, as I mentioned, it can affect the packing density at the interfaces. So we see a relatively positive correlation between surface tension and molecular weight. And the smallest molecules resulted in the lowest surface tension overall. As I said, foaming can be important in terms of area training, and we see that square of foaming capacity, the initial foaming, is correlating pretty well with the area training prosody. Another interesting observation is that our stability factors, which are the foaming stability and contact angle,
Sorry,
also,
Sadegh, you need to finish as soon as possible.
Yes, also correlated pretty well with the area training prosody. That's it. I want to thank the team that helped this project and the funding source. I'm happy to take any questions.
Fantastic. Thank you very much. We have time for questions.
Hi.
Hi, yes.
Hi, Sadegh.
Hi,
That was really interesting presentation. I really like it. I have one question. How you solve the problem, because your data is low, and for this reason, sometimes you face with, overfitting or underfitting. Can you explain how did you, solve this issue?
Yeah, overfitting is a really important problem that we took a lot of care to address. So we took two approaches. One was we used less models with less parameters. So we didn't use like deep learning or neural networks. Those are not suitable for low number of data. So we use simple linear and nonlinear models that do not overfit the smaller data set. The second approach that we took was to use regularization. So basically we limited the the fitting performance of these models. We didn't let them fit really well. We actually limited their fittingness so that they don't overfit our data. And regularization is actually a built-in mechanism in a lot of smaller data sets that we also used.
Perfect, thank you.
Other questions? Thank you very much again.
Thank you.
Austin. Can you stop sharing your screen, Sadegh? You.
Okay, how are we looking?
Looks good.
Okay. Let me just get my final. Okay. Good morning, everybody. I am Austin Perry. I currently work for Dr. Esbran Daraglu, and the current project we're working on specifically is the International Code Council's new standards for on-site wastewater treatment and systems. So for the last couple of years, we've been working with the International Code Council to kind of update what it is they're trying to do for the 2027 building standards. So a couple of years ago, they put out a call for some help. And what they were looking to do was implement new design, construction, operating, and maintaining standards for private sewage disposal. They wanted to focus on the impacts of climate change, and they wanted to install systems that would be more resilient to extreme weather events. Not immune, but resilient. They wanted to take a global approach. They're the International Code Council, so they wanted to make sure they could get as much of the world on board as they could. And they wanted to address the societal and industry challenges that are preventing standards adoptions across more communities and households and whatnot. So together, with all of this in mind, we kind of came up with some approaches that might be able to solve these problems. Some of the key components that we wanted to address were to identify what the commonly used global on-site wastewater treatment systems are. As you can imagine, some of us are working on some very advanced and novel ideas. That doesn't necessarily mean that it's prepared for the larger global community. So we have to kind of focus on things that are already implemented on some type of scale that's meaningful. We needed to identify the environmental and socioeconomic constraints preventing adoption. And what we wanted to do was create pathways for standards adoption and adaption. So some of the challenges, just very generally in residential wastewater management, the community-centered sanitation solutions. So what do we mean by this is to say that we can come up with a system, a wastewater system that works very well. It works perfectly. Because it works perfectly for us doesn't mean it works perfectly for somebody else in a different environment in a different part of the world. They may have different priorities. They may have different objectives. Whatever it might be, what works for us doesn't necessarily mean it works for somebody else. So the idea is whoever it is you're working with, they need to kind of take the lead on what it is they're trying to accomplish. And then we can find the systems that will help accomplish those goals. And then we want to focus on strategic investment and implementation. So one of the things we have to overcome is just a broad understanding of how to finance and fund these types of wastewater treatment systems. It can be challenging, but also if you simplify it well enough, it can actually be very straightforward and help you kind of progress the development of your systems rather quickly. So it all kind of boils down to international objectives and local priority. So some of the international objectives you might hear are things like, hey, let's turn our wastewater into drinkable water, or let's turn our wastewater into water for irrigation, whatever it might be. You can come up to a community and say, hey, we're going to turn your wastewater into something you can drink. Therefore, we will reduce water scarcity and improve water resilience. Unfortunately, for better or worse, there are plenty of communities out there that have a million different reasons to say, I know at some point that this was wastewater, and under no circumstances will I treat this as regular drinking water, no matter what you do to it. I'm not going to do it. So even if you try to achieve this great goal of potable water reuse, there are still some people that are just absolutely no about it. So we have these international objectives, but we also have these local priorities, and you kind of have to meet them, where they are. So in the international community, since this is the International Code Council, kind of piggybacked off of the UN's Sustainable Development Goals. And not going too deep into this, but it was basically, back in 2015, all the countries got together at the Paris Climate Accords and said, hey, look, we'll sign up to do these SDGs, make some improvements on them, and hopefully when we meet back, the world will be a more sustainably developed place. The one topic is clean water and sanitation. And amongst the goals that they're trying to get after in the global sense, they want to reevaluate wastewater management. They want to highlight the importance of water resilience, and they want to address system vulnerabilities, all things that we want to address in the ICC standards update. So some of the resource constraints and adoption barriers we have to kind of contend with are objectives vary based on circumstances. So if you can imagine, in certain places on planet Earth, the simple just collecting and disposing of wastewater is the big idea. That's as far as they may be able to take it. Where in other places, North America, Middle East, taking wastewater and turning it into fresh water would be the big goal to lower water scarcity and improve water resilience. So one of the big constraints is capital in all forms. And what I mean by that is financial capital, human capital, manufacturing capital, on and on and on and on. There's dozens and dozens of forms of capital. All of them come into play. And then you have your socioeconomic limitations. These are things like education. These are things like governance and workforce, all things that we're working on. Myself and Dr. Amroun, we're the University of Miami, so we can do some education. ICC is the standards, and we're having our workforce development program identify where these gaps are in the workforce so that we can develop the workforce so that if and when these standards do get adopted in places that may have never had standards before, we can show them how to develop the workforce that they'll need to support those standards. And maybe we sit here and say, we're not trying to hit a home run. We're not trying to take what they use on the International Space Station to some remote place in sub-Saharan Africa. That's not gonna necessarily work. So maybe it's just incremental improvement after incremental improvement after incremental improvement over enough years, and you get to where you're trying to go. One of the other things that we're trying to work on with the International Code Council is paying a little bit more closer attention to the gender roles in some of these places, where if you are a woman, and for example, if you're going through your menstrual cycle, and you don't have the proper wastewater and sanitation facilities at, say, your school, well, the likelihood of you getting teased probably goes up. The likelihood of you not returning to school to get your education probably goes up. Same thing with the workforce. If you decide you don't want to work there anymore because you're getting harassed or whatever the case is, you don't go to work. All of these things impact the money coming in, the education levels, and the sustainable development trajectory of those communities. So one of the things that we're looking towards in working for the International Code Council and the standards is how can we implement some level of, say, dignity and privacy for women? How do we keep them in school and in the workforce? And how do we prevent them from kind of getting exposed to more health risks than are necessary? So as an example, if there are no wastewater facilities, open defecation is essentially what's going to happen. Women might wait till the early mornings or at nighttime to where they might have a little bit more privacy, but that exposes them to animals. If somebody's walking by, gender-based violence. So it's these things that just create a system, create a structure, a system that might have a lock, and you've got yourself a wastewater system that's more appropriate for women, and the developmental trajectory takes off after that. Some of the environmental threats that we're looking at, so rapid changes in the local environment. We're looking at temperature, precipitation, and wind, and we're looking at how they impact the system as a whole and the various system components within it. So what we ultimately want to do is empower communities for global health improvements. So there's a complex challenge of wastewater and sanitation. We want to empower the community to take this on, because once the community takes it on, that's where resilience really gets built. We want to create a pathway forward. So no matter where you are, you understand where you are, and you understand the challenges that lay ahead of you should you want to improve your wastewater treatment systems. And of course, meet people where they are. So some of the solutions you might see, or we might reference, are everything from advanced toilets like this composting. This is an incineration toilet, but you also have advanced composting toilets. You might have some type of modular design or vermin composting using animals to digest your waste. Lagoons or cat holes like you see hikers and backpackers use. All of these things are systems, but some are better than others. Some treat better, some provide some better output, whatever it might be. The point is, all of these are options, but not everyone knows that they're options. So our goal is to say, hey, here are some options that work in a similar type of environment with a similar type of people. Maybe they'll work for you, but it's ultimately your decision on which one you pick. So what we came up with is a framework called the Wastewater Infrastructure Simplified for Everyone, WISE. So when I talked about capital and how those are the challenges that need to be overcome, we've kind of summarized in these gates, these 6 gates. Each gate has 3 levels, if you can imagine basic, intermediate, and advanced. The first one is foundational knowledge and awareness. So if you can imagine, okay, I know wastewater is bad. I should separate it from where I live, where I sleep, where I eat. That's perfect. That's a very basic understanding of wastewater. But that is different than, say, an advanced, where you can have the 3rd, 4th, 5th order impacts of not treating your wastewater. All of those, so you have the 3 levels for 6 gates. So you have resource availability and economic viability. Essentially, do you have money? Your workforce, do you have the workforce to support these systems? Is it appropriate for the local environment? Who's in control of overseeing that this is implemented correctly? And is this an appropriate one for the people that are going to be using it? So we call it cultural acceptability. This can be one person, this could be a household, this could be a whole community. They just need to be on board and have some buy-in to know what they're doing and that they agree that this is the way they want to go about it. So this is how it would look. And this is an old image, so please don't use this as some sort of factual thing. But this is just kind of a representative example of what it is we are going for right now. If you look on the left where it says natural systems branch, you'll see 3 of the icons, or you should say each icon should show up 3 times, indicating each of the 3 levels. So at level 1, if you were before level 1, think level 0, think open defecation. Once you reach level 1, you get to these very basic systems like basic pit latrines. Should you want to move past it, you have to overcome these gates. If you don't overcome these gates, the system that is beyond these gates will be a little bit more challenging to sustain over a longer period of time. So basically this says, look, once you identify the gates that you need to overcome, you can start working towards those gates in a targeted manner. So you can focus your resources, time, energy, and effort into specific improvements rather than just a broad swath of just make everything better. So what would that ultimately look like? So we created this heat map for on the y-axis, you have various wastewater systems. On the x-axis, you have the gates. If you're at gate 1, those are the kind of systems that you would probably be more expected to be better at using. Gates 2 open up more systems that you'd be more apt in using. And then once you reach the 3rd gate, you can pretty much pick any system that you want because you have the workforce, the money, the resources, and the capacity to achieve such things. And then if you asked, hey, what are the basics? Like if we had to just choose from open defecation to some type of standard, what would you choose? Well, we'll piggyback off the military. The military does all these types of low income, low capacity types of wastewater treatment systems, very easily adaptable to many different types of environments. So what you end up having is a whole host of low capacity types of systems to get people any type of wastewater system. So if you steal the good ideas from the military, you'll have a bunch of people that are able to design these types of systems, and then they'll be on their pathway to more advanced systems once they understand the gate structure. So ultimately, in conclusion, what we're looking to do with the ICC 825 standards is create a structured framework, a clear pathway for increased developmental trajectory. We want to have a long-term impact, improving access over time, and mitigate climate impacts. And then, of course, promote dignity, make sure everyone's got access to wastewater so that the public health improvements can be made, educational improvements, workforce improvements, et cetera, et cetera. So that's what we've been working on. I appreciate you all listening. If you have any questions, feel free to reach out. I'd love to hear what you all think. Thanks so much.
Thank you. We have time for a couple questions.
Sorry to interrupt, but I just joined because I had some other commitment, search committees and so on. I love the fact that we're doing this. Yeah, I think all the students should, try to practice this kind of skill because it's crucial for their career. And also cross-fertilization, right? Getting to know what others are working on, maybe new ideas will emerge. Sorry, Dr. Soleimani, did you find this useful?
Oh, I think this is fantastic. I think this is super, super useful. I love it.
Good, yeah. But is this recorded?
Everything is being recorded, yes.
Okay, okay.
Normally we don't record the Q&A, but in this case we are because we're doing, 4 presentations with Q&A in between.
I think over time we'll make this a requirement for senior PhD students.
Yeah, let's, I think we can discuss a little bit more in our faculty meetings. Any questions? Austin, I'd like to thank you again. I think that was a very, very interesting presentation. I want to chat with you later at some point about how some of this could be applicable in places like India, where I'm from.
Absolutely. Let's do it.
Thank you very much. Kyrah, all yours.
Okay, can you see my screen?
It's perfect.
Perfect. Okay, so good afternoon. My name is Kyrah Williams. I am a double alumna of the university. I have returned for my PhD in civil engineering under the supervision of Dr. Sadegh Tale. I am hoping that with my research, I'm able to create an equitable and sustainable future for all within the built environment, and I'm excited to share my research with you all today. So the title, yes, a comprehensive analysis of water conservation in context of 4 cities. However, today I will be focusing on Houston, Texas, and I'll get to it further along. To start with, the operative goal is to figure out how can we mitigate water scarcity by decreasing our water consumption through using water conservation methods. So to get a better understanding as to where we are today, it's best that we go ahead and look at what is actually occurring. So currently there's approximately 2.5% of our Earth's water is fresh water, and actually less than 0.5% is readily available for potable consumption. For those who may not be aware, or for further clarification, potable water is water considered safe for human consumption, whereas non-potable doesn't meet the safety requirements. With that being the case, it is very paramount that we figure this problem out as soon as possible. Currently, there's approximately over 2 billion people who are currently faced with water scarcity, and over 40% of the world's population is expected to experience some sort of water stress or water scarcity. As mentioned by my colleague, the ICC, the International Code Council, has been developing certain frameworks in order to actually figure out how to mitigate this situation. They created the IWCCP, which is the International Water Conservation Code Provisions, which is a method to standardize to enhance water conservation methods across cities. Being that all cities are not necessarily equal, this will probably help to make that possible. As a result, for our study, we actually focus on 4 cities across various ASHRAE zones: Las Vegas, Phoenix, Houston, and Des Moines. All of these cities, they are similar, their climate zones are similar, but yet they are still very different. As mentioned earlier, I will be focusing on Houston and assessing their water needs. So in the first phase of our research, we focus on single family homes. Focusing on single family home, we got the average input of, okay, there's an average house size of 1750 square feet, 2 stories with an attached garage, and having 3 bedrooms, 2 bathrooms. In phase 2 of our study, we focus on multifamily construction. It gets a little bit iffy or a little bit difficult because all multifamily construction across all the cities are not the same. So I had to figure out how can we actually decipher and figure out how can we have some sort of standardized approach for this project. So I decided to choose garden style homes, mid-rise homes, and high-rise properties, all with focusing on an average dwelling size of 875 square feet with 2 bedrooms, 2 bath, but of course varying in nature in terms of height, where garden style homes have, I would say, 3 stories in height, mid-rise 7 stories, and high-rise properties having 20 stories in height. Now, being that, of course, again, you have to have some sort of standardization. So properties with 20 units or more were evaluated for this specific study. So focusing on the International Water Conservation Code provisions, the IWCCP, there are various, the screen does not actually depict all of the conservation measures. These were the ones that caught our attention. However, the 4 that are circled in blue, where I would consider the quote unquote low-hanging fruit, where these are methods that we can actually implement initially and to actually like, okay, well, this can actually do something for this building typology versus another and can actually help us conserve water within the city. So those 4 are the implementation of water efficient fixtures, gray water systems, rainwater harvesting, and HVAC condensate recovery, which I'll later go into detail once I get past this screen. So looking at the US Census Bureau, I needed to get an understanding as to what is the population density for Houston, Texas, with an average household size of 2.52 people, and also looking at the demographics and how things are sorted between each building typology. So using CoStar, which is a real estate platform, I managed to get the number of properties that currently existed and ultimately arriving at the average number of units for each building typology, which will help as I continue on with this presentation. So for garden style homes, 739 dwelling units, mid-rise 247, and high-rise 308. So in order to get a better understanding as to how much water is actually being consumed within a property, or actually just simply within a household, I needed to achieve the baseline consumption. The numbers that you see on the screen here are what is actually already printed, what is in use in terms of the maximum flow rate and the consumption, as well as the total estimated usage per day for each of these plumbing fixtures or fittings. So taking that information and what I've gathered, I had to come up with a baseline consumption for each household size within the garden style, the mid-rise, and the high-rise properties. Looking at the garden style property for an average household, for example, looking at the lavatory faucet, taking the household size, multiplying it by the maximum flow rate consumption of 2.2 gallons per minute, times the total estimated usage of 3 minutes, times the average number of units for one property is 739 units. I managed to achieve 12,291 gallons per day. So doing that, going through each fixture, getting a better understanding as to what we're actually dealing with for consumption for one household for a garden style property. Now, moving forward into our conservation measures, starting with the rainwater harvesting, I had to reach out to the NOAA in order to find out what the annual or the monthly precipitation totals were for specifically Houston. Acquiring this data, understanding the 5-year average, approximately 46 inches per year fall in Houston, Texas. Now, being that there is not a way to collect all the rainwater that falls, a collection efficiency rate of 80% was determined. So based off of the average roof area for each of these building properties, we managed to achieve the maximum annual harvesting potential, which you see depicted here. Now, one thing that I would like to make note of is a lot of things needed to be cross-checked, a lot of things needed to be verified. But one thing that was able to stand out is looking at garden style, mid-rise, and high-rise. The average roof area definitely changes across the building typologies. Yes, garden styles may be low in number, but however, they cover a much larger parcel of land, hence a larger roof area, which would allow it to actually harvest more or have a higher harvesting potential. Whereas with mid-rise and high-rise properties, the higher you go up, the smaller the roof area. And as you see, those numbers are right in line. So moving forward into I had to still do the calculations for the rainwater harvesting. As seen on the screen, you see that we focus on what the indoor landscaping non-potable consumption and what we're actually able to harvest. These calculations were also performed for each of the building typologies. But I'll go ahead and move forward into the next conservation measure. So condensate harvesting. As a result, not many people understand that the water that is actually created from the coils of an AC unit can actually be reused. The water is typically dispersed into the ground. However, that water can be harvested for other uses. So focusing on what the cooling degree days, the monthly average temperature, as well as estimating the cooling capacity, we were able to establish an estimated condensation production for each building typology as shown on the screen. In terms of the third IWCCP conservation measure, the water efficient fixtures, focusing on this particular measure is deemed much more important, not to discredit the others, but this one actually showed us something that is very paramount, something that should actually be utilized. And to just go into more details specifically about this one, having that this is the numbers that are actually created, looking at the numbers that are depicted for the gallons per household per day, the gallons per property. For instance, looking at the gallons per multifamily residential property, we're looking at an estimated total of 131,000 gallons per day. However, with the IWCCP, creating the numbers and establishing a difference in the maximum flow rate or consumption, the numbers that are highlighted in red, that number is actually approximately 106,000 gallons per day for the gallons per multifamily residential property per day. So the implementation of the IWCCP conservation measure actually have shown to improve, just with this one measure alone, roughly changing 20%, just based off of those changes of those provisions being included. But lastly, focusing on gray water. Gray water, we're looking at consumption, where gray water is the water closets, the irrigation of water that is being used to water your landscaping. We also looked at how can we harvest the water from our plumbing fixtures, as well as the
Sorry,
condensate.
to finish in a minute. Thank you.
Yes, no problem. Looking at the gray water harvesting, we're able to also come up with those water savings as shown on the screen. But the overall summary and takeaway is simply that the implementation of water conservation measures are not without reach. That is actually very helpful, is very useful. And if you see on the screen, the bar chart that's located on the right, and as I flip over to the next one, you'll see that the implementation of these measures, the yellow, gray, and the orange and blue, it actually, you can see the difference as to how these different measures actually show up in specific cities. So again, for Houston, based off of all of our calculations and our forecasting, there's a conservation possibility potential of 697.9 billions of gallons. Again, like I stated earlier, this was done across across 4 cities. And again, it's not a one size fit all. Different measures work for different cities. And yes, I would like to, now, if you have any questions, I'm good. I'm done.
Thank you very much, Kyrah. So sorry for cutting people off, but I do want to kind of stick to time. We are a minute over, but that's okay. I would like to hear any questions from the audience. Thank you again, Kyrah.
Thank you.
So quick question from my side. I mean, you've collected, or it looks like a lot of data, etc. How easy is it to generalize this across the US or other locations?
I personally would say that it was difficult in the beginning, only because, as mentioned, all of the different each city is not the same. Building typologies are not the same. So to find some sort of commonality between those four cities was a bit difficult, but I think that just coming down to low rise, mid rise, high rise, and then just stating, for instance, the 20 units per property was a lifesaver, because at least that's something that we can actually work with. I think that, for instance, instead of looking at just Miami because we are in Miami, this can be something that can be applied to any city. It's just a matter of people taking the time to actually look into it and actually wanting to investigate what works best for them.
Understood.
Thank you.
We have.
Sorry, I do have a question,
Yes.
which is the intellectual merit of the work, right? Like how, I mean, yeah, somewhat similar to Dr. Suranani said, how do you generate transferable knowledge, right? Like, do you end up building some sort of model or doing some sort of statistical analysis? That part is unclear to me. Yeah, intellectual merit. Maybe think about it. Yeah.
I can maybe add a little bit, because I think Kyrah is a bit rushed, so didn't really go into one of the last slides, for example, that you were seeing some of the graphs. So it actually looks at there is a significant amount of modeling involved when it comes to replication and the scalability. So we actually look at 5 years of construction data that represents a particular building topology in each one of those cities, and establish a construction trend and market availability of that particular topology. And using that graph, we predict if the construction trend or the economic development in that region were to continue on that trajectory, what is the potential of that city for the next 5 years or the next 20 years. And we have an upper bound and a lower bound. And you can clearly see also how some cities have a much robust construction sector compared to others. You can clearly see in some cities, you might see that trajectory being more focused on single family residences, where in other cities, you might see it more on high-rise type building topologies, which then gets modeled accordingly. And like, to give you an example, we had an example from City of Phoenix, where the City of Phoenix had gone into moratorium because they could not meet the demand, water demand, if they continued building. But through this, now they're all of a sudden able to kind of create a pathway for how they could continue building or economic development and growth in that city. So that, I hope that gives you a little bit of an insight, but there is a whole modeling aspect of this that we didn't really get into in this presentation.
Thank you, Dr. Androglu. One last comment on this one is, when you get into a model, I would suggest adding some probabilistic distributions to each factor so that the model has some level of reliability or sensitivity analysis. Anyway, we can talk offline.
Yeah, we do. And that modeling aspect actually is Dr. Erkac is our collaborating partner in that project. Yeah, okay. We have a lot more details on that we could share.
All right, great, thanks.
Fantastic. Any last words? Great. Well, thank you very much to everyone. We can discuss more how we want to do this, but I hope this was a useful experience for everyone. Thank you. Have a nice day. Bye-bye.